This is a complicated problem with planar symmetry. It's complicated because the charge density is non-uniform. Since I have solved an example of a non-uniform charge distribution in these two other symmetry kinds, for the sake of completeness, I will also solve an example of such problem, and which is that problem. And so as a result, because of that reason, I'm solving it, but I would like to be as quick as possible in obtaining the final results. So, but first, let me describe the situation. So we have a slab in here. It's an infinite slab. A is its thickness. But as usual, we start the origin. We choose the origin somewhere in the midplane in here, and we choose the z-axis perpendicular to the plane. So that means these two distances are a over 2. I mean, the surfaces are at the coordinates z equals a over 2 and minus a over 2. What's the charge density? The charge density at point x, y, z is given by this expression. The charge density depends only on the z coordinate. Where here B is just a given constant, so we have to express everything in terms of B, and we would like to find the electric field. Right. At this point, let's just explain if this charge distribution has planar symmetry or not. So one of the important points is that it doesn't depend on x and the y coordinates. This is consistent with the planar symmetry because let's say this point in here, which is at a distance z, so just consider another point which has the same z coordinate but with different x and y coordinates. So these 2 points can be obtained by translating one to the other along the xy plane. And by symmetry argument, of course, the charge density shouldn't change under size transformation. So we should have the same charge density at that point as the charge density in here. This implies that the charge density does not depend on the xy coordinates. So that condition is satisfied. There is another symmetric condition, z goes to minus z. So that's basically a reflection. So this point and that point, this point has a coordinate, let's say, has Cartesian coordinates x, y, z. This has Cartesian coordinates x, y, minus z. So I'm just replacing z coordinate with minus z, and then I go to the reflected point. So the charge density at the reflected point should also be the same as this one. So that's part of the symmetry. So this would imply that this rho is actually an even function of the z coordinate. So as a result, I can solve the problem with this. This has the necessary symmetry. But if this was an expression like b times z, in that case, such charge distribution would not have the necessary reflection symmetry. And we won't be able to use the method that we are using directly for such problems. Okay, so as a result, this charge distribution has the necessary planar symmetry, and we can apply Gauss law. So there's no problem with the Gauss law. Only in the integration of the charge density we have to evaluate an integral. Let's remember this. So as a start, let's just take a point outside. So z is the coordinate of that point. Let's remember that if I just choose another point with a coordinate minus z, in that case, the electric field in here is has the same magnitude as the electric field in here, but opposite direction. In any case, let's just show it like that. And to find the electric field in here, we just choose a Gaussian surface that passes from that point and also passes from this reflected point in here. So let me try to draw it like that. Okay, so therefore this is a Gaussian surface with a height which is equal to 2z. And well, there's a base area in here, so I'm going to use the capital A to represent the base area. So let me say it like this. For a point outside, I'm just going to say that z is bigger than a over 2. By this choice, I'm also choosing z to be a positive number. So I'm going to treat z as a positive number from now on. In any case, let's just write down the Gauss law. So we have the flux integral is equal to the enclosed charge divided by epsilon 0. The left-hand side, I'm not going to repeat the whole argument. The left-hand side can be expressed as 2 times the flux through the base area in here. And the only difficulty is in evaluating this right-hand side. And in here, for the enclosed charge, I have to do some kind of an integration in here. So somehow I have to divide these charges into small pieces and then integrate. So how do I do this? But first, let's just recognize this. All the enclosed charge is within that region, right? So therefore, this is on a cylinder with base area A, but with a height which is equal to A. Okay, let's remember this. But since the charge density is not uniform over that region, I cannot multiply a charge density with the total volume of that region. What I need to do is this. I just consider a small disk in here with a very small height, infinitesimal height actually. And let me actually consider it like this. We just consider all the charge between the coordinates z prime. I need to use z prime because I have used z before. All the charge between the coordinates z prime and z prime plus delta z. Dz, sorry. So dz prime, because this is a differential. So I'm just going to assume that the thickness of that disk is infinitesimally small. In any case, because of the symmetry, I know that the charge density has the same value everywhere on that disk, and so therefore I can write down the amount of the charge on the disk as charge density multiplied with its volume, and the volume in that case is given as the thickness of the disk multiplied with the surface area of the disk. And finally, we just write down the expression for the charge density, which is b times z prime squared multiplied with this. All right, that's basically what I'm going to do. So therefore, this is an integral of ba times z prime squared dz prime. What are the limits of the integration? Well, basically the charges start from here. So z prime should start from the point minus a over 2 and should end at the point plus a over 2. So therefore, this is an integral from minus a over 2 to plus a over 2. So let me quickly do this calculation. So that's 1 over epsilon 0. So BA is a constant that I take it out. And then we have z prime cube over 3 is the integral of the function. And the integration bounds are plus a over 2 and minus a over 2. So as a result, at the upper limit, this function is equal to 1 over 3 a over 2 cube. And at the lower limit, it is 1 over 3 minus a over 2 cube. So you can easily see that this whole thing is equal to 1 over 6 a cube. And so therefore, the right-hand side is ba little a cube divided by 6 epsilon 0. And the left-hand side is 2ez times the area. The base area cancels. And so therefore, we get the electric field as outside as b times a cube divided by 12a0 epsilon 0. Okay, it's again constant independent of c. All right, we have discussed this thing before. For an infinite plane, we have said that the electric field produced does not depend on the z coordinate. Well, for positive values of z in any case. For any kind of an infinite slab, we also had the same behavior. And then we have said that at some point I can also express this as like some kind of a surface charge density divided by 2 epsilon 0. And by looking at that expression, you can then compute the corresponding surface charge density in here. In any case, so that's not the part that I'm going to discuss. So then let's go ahead and then compute the electric field inside the slab. And let's see how it goes. So therefore, I have a point somewhere in here. and I need to find the electric field at that point. And then I consider the corresponding reflected point and then the electric field in here, whatever. And I choose my Gaussian surface as a cylinder like that. Again, let me try to show the base surface like this. Even though this is a side view, I need to use these kind of techniques to do this. So in any case, the right base of the Gaussian surface is at coordinate plus c, and the left base is at minus c. So these are going to be our integration bonds basically. The surface area of the base is again A, right? Let me write down this mandatory thing. So for a point inside, I'm going to choose the z coordinate to be positive, but that's less than a over 2. So I'm just considering this case. So we write down the Gauss law. On the left hand side, we have the same expression. On the right hand side, I have the integral of somehow the dq, and that's an integral of charge density multiplied with volume again. But I'm just going to write everything in here. Okay, so first, I mean, it is important to remember that we always have this kind of disks in here. And with coordinates between z prime and z prime plus dz prime. It's the same thing again, same integral expression. In any case, the density is b times z prime squared. What's the volume? It is dz prime multiplied with a. And what are the integration limits? It's basically from minus c to plus c. All right, so all of the charge in here should be included. And so therefore my z coordinate integration starts from the left base and ends up at the right base. All right, so that's 1 over epsilon 0, b times a, and then I have the z prime cube over 3 integral, and evaluate between plus c and minus c. So that's equal to 2z cube over 3. Just compute this. And I have 2ez times a on the left-hand side. The base areas cancel. 2's cancel. And so therefore ez is equal to b times z cube divided by 3 epsilon 0. I'm checking if I made a mistake. So let me remember the previous expression. There should be some kind of a continuity. Yeah, I made a mistake in here. Sorry about this. So this has to be 1 over 12. And so that's 1 over 12. And so therefore this is 1 over 24. Okay. At least I discovered the thing. So with this, you can check that this is indeed continuous. So therefore, this is what I'm going to say. The electric field, z component of the electric field is, I can write it in that form. It is b times z cubed divided by 3 epsilon 0. So let me say this is for z is less than a over 2 and bigger than 0. And outside it was b times a cube divided by 24 epsilon 0. So that's for z is bigger than a over 2. In any case, I can extend these results to the negative side easily. So I know that this is an odd function, so therefore I can easily extend this to minus a over 2. And if I use an absolute value sign in here and a signum in here, I can also extend this to the negative side as well. In any case, if I plot this function as a function of z, I try to draw the straight lines, but sometimes it's not possible. So that's the point a over 2, and that's the point minus a over 2. And I'm going to use the blue color. So outside, the electric field is constant on the left side of the slab as well. The electric field is constant. Inside, the electric field goes like z cube. And the electric field is continuous. You can check the continuity by just looking at the expression in here. When z is equal to a over 2, you can check that these two expressions give you the same value. Okay.